This series of lectures has to do with Module 1 in NRES 450, Biology of Wildlife Populations. In this section, we're talking about estimating abundance. Why do we estimate abundance? Abundance is the fundamental metric of population dynamics. The study of population dynamics is the study of how the abundance of a population changes over time. So before we can study how the population changes over time, we first have to know how many individuals there are. In the past, it was common to use a so-called complete census where every single animal was counted. There's a couple of reasons why we don't do this anymore, but probably the most obvious is that it's very, very expensive. Less obviously, a complete census can be biased if the assumption that you are able to count every single individual is not in fact correct. Often, individual animals that are farther away are harder to see, and this kind of bias in detection or failure to detect individual animals can lead to a biased estimate of your population size. There are two concepts that become important when we're talking about an estimate of abundance rather than a complete census. And these are precision and accuracy. Precision refers to the spread or the scatter of estimates relative to the truth. The target on the left shows a very precise set of estimates, 4 independent estimates that are very close together. The target on the right, on the other hand, shows 4 estimates that are less precise. Each of the subsequent estimates is farther away from the other ones than the target on the left. In contrast, we can also talk about accuracy, which refers to how close, on average, the estimates are to the truth. So if the center of our target is the truth, then the target on the left shows a series of estimates that are less accurate than the target on the right. The ones on the left are, on average, biased away from the truth, the center of the target. The ones on the right, on the other hand, are more accurate because the average of those estimates is closer to the center of the target, the true value that we're interested in. Often there's a bit of a trade-off between achieving precision, the target on the left, and accuracy, the target on the right. Most of what we're going to do in this course is going to revolve around estimating the precision of our estimates and worrying less about the accuracy. Accuracy comes from the nature of how you sample your population, and for the simple sorts of estimates that we'll be doing in this course, it's relatively easy to get an unbiased or accurate, on average, estimate of a population size. We'll leave the question of how to do accurate or unbiased estimates in real populations for other courses. Here are a few terms that we will use throughout our discussion. Imagine we have a landscape with 100 individuals spread around on the landscape. An element is an individual in this case. These are the things that we are counting. We also have the target population. This is the population of elements about which we want to make inferences, in particular, about which we want to estimate its total size. The red box describes the target population in this case. We're going to divide up that target population into sample units. In this case, I've outlined a single box on our target population, 1 out of 100 sample units that we could choose to use in our estimation procedure. In this case, all the sample units are the same size, but that's not necessary. We can also refer to the sample frame, which is the total collection of units, sample units, that we use. In the easiest case, the sample frame and the target population are identical. However, it's possible that the sample frame is not the same as the target population. For example, there could be a block of private land which we do not have access to. We won't be able to access these individuals to count them. And the sample units that overlie that private land will not be available for selection in our estimation procedure. Now that we've defined our sample frame, we have to answer a second question, which is whether we're going to sample with or without replacement. Because we're not taking a census, the basic operation is to choose a random sample of the sample units in the frame. Here's an example of 5 randomly selected units from our sample frame. We count the number of individuals inside each selected unit, which gives us data of 1, 0, 0, 1, and then there are actually 2 points in the upper corner here. The important question is, how do we go about selecting these 5 units? We could do it with replacement, which means imagining a box full of slips of paper with a label representing each sample unit on each slip of paper. We draw out a slip of paper, make a note of the number of individuals in that box, and then we put the slip of paper back in. We are replacing the unit back into the sample frame. The other alternative is where we draw out the slip of paper, count the individuals in the square, and then set that piece of paper aside. What that means is we are sampling without replacement, so the size of the population gets a little bit smaller with each subsequent sample. That becomes important when we want to estimate the precision of our estimate, which we'll talk about in a little bit. An important consequence of sampling with replacement is that sometimes you can get the same sample unit counted twice. So in this case, our sample unit right here has been counted twice, and so instead of 1, 0, 0, 1, 2, we have 1, 1, 0, 1, 2. This is perfectly acceptable, and obviously with a small sample relative to the sample frame, the likelihood of this happening is actually quite small. But it's okay. We will keep it in mind whether we sample with or without replacement when we come to calculate the precision of our estimated abundance. In this course, we're mostly going to be sampling without replacement because of the nature of the population samples we'll be collecting makes it difficult to sample with replacement. This is the end of the first video on estimating abundance. In the next video, we will take a look at what we do with those sample counts in order to estimate both the density and the abundance of the individuals in the population.